There is a force running through everything you have ever touched, seen, or imagined, and you have never once held it in your hands. It has no color when it rests. It has no shape when it waits. It has no address, no border, no surface you could press a finger against and say, "Here it is, this is the thing itself." And yet without it, nothing in the universe would ever change. Not a single atom would shift position. Not a single star would burn. Not a single thought would cross the space inside your skull. This force, this presence, this strange and ghostly something that physics calls energy, may be the most important concept in all of science. And the deeper you follow it, the stranger it becomes. Because somewhere between the equations on a chalkboard and the vibrating fabric of space itself, energy stops looking like a physical ingredient and starts looking like something closer to a rule, a law, a structure baked into the grammar of existence. Tonight, we are going to chase it. We are going to follow it from the earliest fires of human intuition, through the laboratories of the 19th century, through the quantum revolution that cracked the classical world open like an egg, and all the way down to the unsettling edge where empty space itself turns out to be seething with a kind of energy no one ever predicted. If you find yourself captivated by what you're hearing, it would mean a great deal to us if you liked this video and subscribed. It genuinely helps us keep exploring these ideas. Let's begin somewhere ancient, somewhere before any equation had ever been written, before anyone had given this thing a name. Imagine a fire, not a metaphor for a fire, but an actual fire in an actual night, 10,000 years ago, somewhere on an open plain under a sky crowded with stars. The people gathered around that fire understood something about it that they could not have articulated in modern language. They understood that the fire was doing something. It was releasing something. The wood went in cold and still, and out came heat and light and the crackling wild motion of flames. Something had changed. Something had moved. Something had been transferred from the wood into the air and into their skin and into the darkness around them. They did not have a word for energy, but they were watching it perform its most basic act. Transformation. That is the first truth about energy, and it has never changed, not in 10,000 years of science. Energy is the currency of transformation. It is the accounting system the universe uses to track every single change that ever happens anywhere. When anything moves, when anything warms, when anything grows or collapses or glows or fades, energy is the quantity that must be counted and balanced. And here is the thing that should stop you cold. It always balances. Always. Not usually, not most of the time. Always. No exception has ever been found. No experiment has ever violated it. In the entire history of physics, across billions of measurements in laboratories and in space, and deep inside particle accelerators, the total account of energy has always come out exactly right. It is one of the most precisely verified facts in all of human knowledge. And this conservation, this perfect, relentless balance, is itself a clue. Because substances do not behave this way. Water can leak, matter can be destroyed, objects can be lost, but energy cannot be created and cannot be destroyed. It can only be moved or changed in form. That is not how substances behave. That is how rules behave. That is how laws behave. Energy, even before we understand what it is, already behaves less like a thing and more like a principle. But let us not rush toward abstraction too quickly. There is a whole rich history to walk through first, and much of that history involves people who thought they understood energy far better than they did. The scientists and philosophers of the 1600s and 1700s built a framework of mechanics that seemed to explain the physical world with breathtaking precision. Isaac Newton laid down his laws of motion, and the world became, in a certain sense, a vast clockwork. Forces acted on masses. Masses accelerated and decelerated and collided and orbited. And woven through all of this was a quantity that kept the books balanced: energy. Kinetic energy. The energy of things in motion, measured neatly by mass and velocity. Potential energy. The stored energy of position, measured by height and gravitational pull. And when one transformed into the other, the sum stayed constant. A cannonball fired upward slowed as it climbed, trading kinetic energy for potential, then fell and traded it back. A pendulum swung back and forth, endlessly exchanging the two forms without losing a drop. The math was elegant. The predictions were accurate, and this led many thinkers to a very natural assumption. Energy must be something. It must be a substance of some kind, even if invisible. Perhaps it was a fluid. Perhaps it was carried in the motions of invisible tiny particles. Perhaps, like heat, it was a kind of material that flowed from hot objects to cold ones. Indeed, for a time, heat was believed to be exactly that, a fluid called caloric, which flowed from warm bodies to cool ones, like water flowing downhill. This was not a stupid idea. It explained a great deal of what people observed. Warm objects did seem to lose something as they cooled. That something did seem to flow into the cooler environment. The caloric theory was tidy, intuitive, and plausible, and it was wrong. The experiment that destroyed it was almost comically direct. A military engineer named Benjamin Thompson, working in a cannon factory in the late 1700s, noticed that the process of boring a hole through a brass cannon produced enormous amounts of heat, far more than the caloric theory could account for. If caloric was a fluid contained within the metal, it should have been exhausted eventually, but the heat just kept coming. Thomson submerged the cannon barrel in water and used the heat generated by boring to actually boil the water. He could generate apparently unlimited heat simply by continuing to bore. There was no caloric fluid being liberated. There was only motion. Mechanical motion, the rotation of the drill, was somehow becoming heat. Energy was not a substance that objects possessed in fixed amounts. It was a convertible quantity. It changed form, and when you drove motion into matter, that motion became heat. The fluid theory died slowly, but it died completely, and in its place grew a new understanding. Energy is not a material ingredient. It is a measure of the capacity for change. That shift in thinking from energy as substance to energy as measure was one of the great conceptual leaps in the history of physics, and it set the stage for everything that came after. Through the 19th century, physics accumulated a picture of energy that grew steadily more precise and more abstract. The understanding of heat deepened enormously. James Joule, a brewer-turned-physicist, performed meticulous experiments with water and rotating paddles, and showed that a specific amount of mechanical work always produced a specific and consistent rise in temperature. The relationship was exact, reproducible, universal. This was the mechanical equivalent of heat, and it proved beyond doubt that heat and motion were not separate things. They were two faces of the same underlying quantity. Meanwhile, thermodynamics emerged as a discipline, and with it came one of the most profound statements ever made about the physical world. Energy is conserved, not as a hope, not as an approximation, as a law. The first law of thermodynamics said it plainly. The total energy of an isolated system does not change. Whatever happens inside, combustion, collision, radiation, chemical reaction, the sum of all forms remains constant. And the second law, which followed quickly, said something even more haunting. While total energy is conserved, its quality degrades. Useful, concentrated energy spreads out. Order bleeds into disorder. A hot object cools. A sharp temperature difference smooths away. The universe, left to itself, drifts toward a state of maximum spread, maximum disorder, minimum useful energy. This tendency, what physicists call entropy, revealed something profound about energy's nature. Energy was not just an amount. It had a direction. It had a tendency. It preferred certain arrangements over others, and that preference was irreversible. You could not easily convert disordered thermal energy back into concentrated mechanical energy. The arrow of time was written in the behavior of energy. So here, near the end of the 19th century, physics had built an impressive and coherent picture. Energy was conserved. It came in many interchangeable forms: kinetic, potential, thermal, chemical, electromagnetic. It could not be created or destroyed, and it had a preferred direction of spread. The picture was not perfect, but it was powerful. It explained engines and refrigerators and chemical reactions and electrical circuits. It seemed to be a complete theory of energy's behavior. And then, without warning, it fell apart. Not entirely, but in a way that revealed it had been built on assumptions so deep that no one had even noticed they were assumptions. The assumptions were about continuity and about smoothness. The assumption that energy could take any value, that you could always have a little more or a little less without any restriction. that the universe was, at its core, a smooth place where quantities varied in gentle, unbroken ways. Those assumptions turned out to be spectacularly, profoundly wrong. The fracture began in a place that seemed far removed from deep philosophy. It began with light and with heat. Specifically, it began with a question that physicists in the 1890s were struggling to answer. How does a hot body glow? This seems like a mundane question. Heat a piece of iron and it glows red, then orange, then white. Simple enough. But when you tried to calculate exactly how much radiation a hot object should emit at each frequency, using the best tools classical physics had, something went terribly wrong. The theory worked perfectly at low frequencies, but at high frequencies, it predicted that a hot object should emit infinite energy. Not a lot of energy, infinite. At every temperature, into every glowing object, the theory inserted an infinite amount of energy at short wavelengths. Physicists called this the ultraviolet catastrophe, which is a wonderfully dramatic name for a wonderfully catastrophic failure. Hot objects in reality, of course, do not emit infinite energy. They glow normally, with a smooth peak and a fall-off at high frequencies. The universe was clearly not listening to the equations. Something was preventing all that high-frequency energy from appearing. Something was cutting it off. And nobody knew what. Into this crisis stepped a man named Max Planck, who was not looking for a revolution. He was a careful, conservative physicist who wanted to fix a specific technical problem in the radiation formula. He tried everything he knew, nothing worked. And finally, in a move he later described as an act of desperation, he introduced a radical assumption. He proposed that the energy exchange between matter and radiation could not take on any arbitrary value. It had to come in specific, discrete packages. The energy of each package was proportional to the frequency of the radiation. High frequency meant high energy packages. Low frequency meant low energy packages. And the constant of proportionality, the size of the basic package, was a new fundamental number that Planck calculated from his formula. We now call it Planck's constant, and it is one of the most important numbers in all of physics. When Planck plugged this assumption into his equations, the catastrophe disappeared. The formula matched the observations perfectly, at all frequencies, at all temperatures. It was an extraordinary triumph, and Planck himself was deeply uncomfortable with it. Because his assumption implied something unsettling, the universe had a smallest unit of energy exchange. Below that unit, transactions were simply not permitted. Nature had a minimum denomination. You could not pay less than the minimum. You could not shave energy into arbitrarily thin slices and hand them out one gossamer sliver at a time. Energy came in packets, in quanta. The word quantum, from the Latin for how much, entered physics and never left. And with it came the first tremor of the revolution that would shake classical physics to its foundations over the next 3 decades. But Planck's quantum was, at first, almost a mathematical trick, an uncomfortable and successful trick, but still something that could perhaps be explained away, perhaps interpreted as a feature of the way atoms in a solid vibrate rather than a fundamental statement about the nature of energy itself. That interpretation became impossible to maintain after 1905, when a young patent clerk in Bern published a paper on the photoelectric effect that would, decades later, win him the Nobel Prize. His name was Albert Einstein, and the paper was not his famous theory of relativity. It was something even more conceptually radical. The photoelectric effect was a phenomenon that had been observed for years without anyone being able to explain it properly. When you shined light on a metal surface, electrons were knocked loose. Fine. But the details of how they were knocked loose refused to make sense within classical physics. The number of electrons released depended on the intensity of the light, but the energy of each individual electron depended only on the frequency of the light, not the intensity. And if the frequency was below a certain threshold, no electrons were released at all, no matter how bright the light was, no matter how long you waited. Below that frequency, nothing. Above it, immediate response. Einstein proposed an explanation so simple and so radical that many physicists refused to believe it for years. He proposed that light itself was made of discrete packets of energy, that it did not travel as a smooth, continuous wave delivering energy gradually across a surface, but as individual particles, photons, each carrying a specific amount of energy determined entirely by their frequency. High-frequency light meant audio high-energy photons. Low-frequency light meant low-energy photons. And if the photons were too low in energy, no individual photon could knock loose a single electron, regardless of how many of those weak photons arrived. The minimum energy needed to free an electron from the metal was a fixed threshold, and only individual photons with energy above that threshold could deliver the blow. This was not just a mathematical convenience. Einstein was saying that light, which Maxwell's equations described as a continuous electromagnetic wave, was also in some sense made of particles. That energy did not flow through light like water through a pipe, but hopped through space in individual, indivisible packages. The wave picture was not wrong, the particle picture was not wrong. Both were somehow simultaneously true. This was the first glimpse of what would become wave-particle duality, one of the deepest and most disorienting features of quantum mechanics. And it made the question of energy's nature suddenly and urgently difficult. Because if photons carried energy without having mass, if they traveled through empty space as individual packets of something that had no material substance, then what exactly was that something? What were those packets made of? The question was not rhetorical, it was desperate. And the answer, when it finally emerged from decades of theoretical struggle, was not what anyone had hoped for. To understand where physics went from there, it helps to feel the full strangeness of the situation. Classical physics had given the world a picture of energy as a smooth, continuous, well-behaved quantity. Quantum mechanics was tearing that picture apart systematically. Not randomly, not chaotically, but with exquisite precision. The new physics was not less precise than the old. It was more precise. Its predictions were often accurate to many more decimal places than anything classical mechanics could achieve. But the picture it painted of reality was deeply, radically alien. Consider the atom. In classical physics, an electron orbiting an atomic nucleus was like a tiny planet orbiting a tiny sun. It could orbit at any distance, with any speed, carrying any amount of energy. The atom was a smooth, continuously adjustable thing. You could in principle nudge the electron into any orbit you wanted by supplying any amount of energy you chose. But when physicists actually looked at atoms, they saw something utterly different. Atoms did not emit or absorb energy continuously. They emitted and absorbed it in sharp, precise bursts at very specific frequencies. If you heated hydrogen gas until it glowed and then passed that light through a prism, you did not get a smooth rainbow. You got a handful of sharp, precise lines. 4 lines in the visible spectrum, exactly 4, each at an exact frequency. Nothing in between. This was the spectrum of hydrogen, and it had been measured carefully for decades before anyone understood what it meant. What it meant, as Niels Bohr figured out in 1913, was that the electron in a hydrogen atom was not free to orbit at any distance. It could only occupy certain allowed orbits, corresponding to certain allowed energies, and when it jumped from one orbit to another, it emitted or absorbed exactly the energy difference between those two orbits, in the form of a photon, with exactly the corresponding frequency, no fractions, no intermediate values. The electron jumped all at once from one allowed level to another, and a photon appeared or disappeared in the process, carrying precisely the right energy. The atom was not a miniature solar system. It was a quantum system, a system with a discrete fixed menu of possible energies and no permission to exist anywhere in between. This was quantization of energy at its most stark and concrete, and it forced physicists to ask a question they had been avoiding. Why? Why should reality only allow certain energies? Why should there be forbidden values? What is actually happening when a quantum system sits in an allowed state? What is the deep structure that produces these sharp, precise levels rather than a smooth continuum? The answer to these questions came from one of the most beautiful and most baffling ideas in the history of science, the wave function. In the mid-1920s, 2 separate and radically different mathematical approaches to quantum mechanics were developed almost simultaneously, and when it was proved that they were equivalent, physics possessed for the first time a complete formal framework for the quantum world. The framework said something remarkable about what it meant for a particle to have a definite energy. It said that a particle or system had a definite energy when it existed in what the mathematics called an energy eigenstate. That word, eigenstate, is a German word meaning something like own state or characteristic state. But stripped of its technical clothing, the idea is this. An eigenstate is a condition in which the system gives a definite, reproducible answer when asked a specific question. An energy eigenstate is a condition in which the question, "What is your energy?" has a definite, precise, reproducible answer. Outside of that condition, outside of an eigenstate, the question has no definite answer. The system exists in a superposition of possibilities, a structured spread of potential energies, none of them actual until an interaction selects one. This is one of the places where quantum mechanics becomes genuinely, irreducibly strange. Not strange because physicists are being sloppy or because the theory is incomplete. Strange because that is what nature is actually like at small scales. A quantum system does not carry a definite energy the way a classical object carries a definite mass. It carries a probability distribution over possible energies, a structured spectrum of what it might reveal, and only when it interacts with something else, only when it exchanges information with another system, does that spectrum collapse to a single definite value. This is not a statement about our ignorance. It is a statement about reality. Before measurement, there is no definite value to be ignorant of. The value does not exist in a hidden way, waiting to be uncovered. It comes into existence through the interaction. Einstein famously hated this. He spent the last 3 decades of his life arguing that quantum mechanics must be incomplete, that there must be hidden variables, definite values that exist before measurement, even if we cannot access them. He and his colleagues published thought experiments and paradoxes designed to demonstrate the theory's inadequacy. Physicists argued bitterly across continents and decades, and the experiments, when they were finally done with sufficient precision in the latter half of the 20th century, sided with quantum mechanics. The world is genuinely, irreducibly probabilistic at the quantum level. Definite values come into existence when systems interact, and not before. Energy, then, is not something sitting inside a particle like a charge in a battery. It is something the particle is capable of revealing under the right conditions. It is a lawful potential, a structured capacity, not a stored thing, a permitted response. This shift from energy as thing to energy as permitted response is one of the conceptual pillars of modern physics. And it is not a step backward in understanding. It is a step forward into a deeper and more precise truth about what nature actually is. But we are not yet at the bottom, not even close. There is something stranger still waiting beneath the wave function and the eigenvalue and the superposition. Something that lives in the concept of the field. The idea of the field is older than quantum mechanics. Michael Faraday, in the mid-19th century, pioneered the concept while studying electricity and magnetism, where his contemporaries thought of electric and magnetic forces as direct actions between charged objects. Faraday thought differently. He saw the space around a magnet as genuinely different from ordinary empty space. The magnet created something in its surroundings, a field that extended through space and could act on other objects placed within it. When he draped iron filings over a paper held near a magnet, the filings arranged themselves into the curves of the magnetic field lines, making the invisible visible in a startling and beautiful way. This was a new kind of physical reality. Not objects, but fields. Not particles, but conditions of space. James Clerk Maxwell took Faraday's intuitions and gave them mathematical form, constructing a complete theory of electromagnetic fields that stands to this day as one of the great achievements of human thought. Maxwell's equations described how electric and magnetic fields generated and sustained each other, and they predicted that these fields could propagate through space as waves even in the complete absence of matter. When Maxwell calculated the speed of these waves, he got a number that matched, to stunning precision, the measured speed of light. Light, in that moment, was revealed to be an electromagnetic wave, a ripple in the electromagnetic field, not a particle, not a fluid, not a substance, but a pattern of change propagating through a field that permeates all of space. This was revolutionary, and it only became more revolutionary when quantum mechanics arrived and the electromagnetic field was quantized. When you take a classical field and apply quantum mechanics to it, you get a quantum field. And a quantum field is something that even today resists easy description. It is not empty space, it is not a substance, it is a physical entity that exists at every point in space and time, capable of being in different states, capable of carrying energy, capable of interacting with matter, and crucially, the particles that physics describes as the fundamental constituents of matter, electrons, quarks, photons, are not tiny solid objects embedded in space. They are excitations of quantum fields. A photon is a quantized excitation of the electromagnetic field. An electron is a quantized excitation of the electron field. A quark is a quantized excitation of the quark field. The particle is not a thing that the field contains. The particle is a thing the field does when the electromagnetic field is disturbed in the right way, when it acquires a specific quantum of energy in a localized region. That localized energetic excitation is what we call a photon. The photon travels through space not because a tiny object is moving from one place to another, but because the excitation of the field propagates. The energy moves through the field the way a sound wave moves through air, as a pattern of activity, not as a transport of material. This picture, quantum field theory, is the most accurate physical theory ever constructed by human beings. Its predictions have been verified to extraordinary precision, in some cases to 10 decimal places. It is the foundation of the standard model of particle physics, which describes every known type of particle and every known force except gravity, and at its core, it says something specific and remarkable about energy. Energy is what happens when quantum fields are excited. It is the measure of how much activity the fields are engaged in, how strongly they are vibrating, how deeply they are disturbed. In the absence of any excitation, when the fields are in their lowest possible state, we might expect energy to be zero. We might expect perfect stillness. But here is where the story takes one of its most astonishing turns. The lowest state of a quantum field is not stillness. It cannot be. And the reason it cannot be is one of the most profound constraints in all of physics, Heisenberg's uncertainty principle. Werner Heisenberg, in 1927, formulated one of the most counterintuitive results in the history of science. He showed that for certain pairs of physical properties, the more precisely you know one, the less precisely you can know the other. The canonical example is position and momentum. The more precisely you pin down where a particle is, the less precisely its momentum can be defined, and vice versa. But the uncertainty principle extends beyond particles. It applies to quantum fields as well. For a quantum field, there is an uncertainty relation between the field's amplitude at a point and the rate at which that amplitude changes. If you tried to force a field into a state of absolute stillness, zero amplitude, zero rate of change, you would need to know both of those quantities with infinite precision simultaneously, and the uncertainty principle forbids it. So, the field cannot rest. Even at absolute zero, even in the complete absence of any particles or radiation, even in a region of space from which you have removed every photon and every electron and every atom, the quantum fields continue to fluctuate. They jitter. They buzz with tiny, unavoidable, uncancelable oscillations. This minimum unavoidable activity is called zero-point energy, and the energy of the ground state of all the quantum fields everywhere in space is called vacuum energy. It is real. It is measurable. It was predicted theoretically before it was detected experimentally, and when experiments were designed to probe it, they found it exactly as described. The most striking demonstration of vacuum energy is called the Casimir effect. If you take two flat metal plates and place them extremely close together in what is otherwise empty space, they will be attracted to each other. Not because of any charge, not because of any magnetic force, but because the vacuum fluctuations of the electromagnetic field are slightly suppressed in the narrow gap between the plates compared to the fluctuations outside, creating a tiny pressure difference. The vacuum pushes the plates together. This is an astonishing thing. Empty space is pushing metal plates together. The energy of nothing is doing work. The vacuum has consequences. When physicists measure this effect and compare it to the theoretical predictions, the agreement is extraordinary. The vacuum energy is real, and its effects are precisely calculable. But this opens a door to one of the deepest unsolved problems in all of physics, perhaps the deepest of all. If you take the predictions of quantum field theory seriously and calculate how much energy the vacuum should contain, You get a number that is either infinite or, if you impose a cutoff at the Planck scale where quantum gravity presumably takes over, you get a number that is something like 10 to the power of 120 times larger than the actual energy density of the universe as measured by cosmologists. That discrepancy, 120 orders of magnitude, is the largest quantitative disagreement between theory and experiment in the history of science. It is called the cosmological constant problem, and it remains completely unresolved. Something is wrong. Either the vacuum energy is being canceled by some mechanism no one understands, or the calculation itself is wrong in a way no one has identified, or there is something fundamentally incorrect about how we are combining quantum mechanics with general relativity. The universe, in other words, is not telling us what we expect to hear. The story of energy, followed to its deepest point, arrives not at a clean answer, but at a magnificent and humbling mystery. Let us take a step back from the technical edge and look at the sweep of what we have discovered. We began with fire, with the oldest human intuition that something is happening, something is changing, something is flowing from one form to another. We trace that intuition through Newton's mechanics, through the thermodynamic revolution, through the discovery that heat is motion and that energy is conserved with perfect consistency across every process in nature. We followed it through the crisis of the ultraviolet catastrophe, through Planck's desperate gamble that energy comes in packets, through Einstein's radical proposal that light itself is quantized, through Bohr's atomic model with its discrete allowed levels and its sharp spectral lines. We followed it into quantum mechanics proper, into wave functions and superpositions, and the discovery that definite energy values are not properties that systems simply have, but properties that systems can reveal under the right conditions. We followed it into quantum field theory, where particles dissolve into excitations of fundamental fields that permeate all of space, and where energy is the measure of activity within those fields. And we followed it to the vacuum itself, to the irreducible buzzing of quantum fields in empty space, to the energy of nothing, to the Casimir effect and the cosmological constant and the largest unsolved problem in theoretical physics. At every step, energy became less like a substance and more like a relationship, less like an ingredient and more like a property, less like a thing the universe contains and more like a rule the universe obeys. And this trajectory is telling us something important, not about our limitations as scientists, but about the nature of reality itself. Reality, at its deepest accessible level, is not made of stuff. It is made of patterns, rules, relationships, structures of permitted change, and energy is perhaps the most fundamental of those structures. The underlying constraint that determines which changes are possible and which are forbidden, which transitions can happen and which cannot, which futures are accessible from a given present and which are permanently out of reach. Consider what it means for energy to be quantized in an atom. An electron in a hydrogen atom can exist at a set of specific energy levels. The lowest, called the ground state, is the state the electron naturally falls into when the atom is cold and undisturbed. The electron cannot simply drift to a lower energy because there is no lower energy permitted. It is already at the bottom. The only way it can change its energy is by absorbing a photon with exactly the right energy to lift it to the next allowed level, or by emitting a photon to drop from a higher level to a lower one. The precision required is exact. The photon must carry exactly the right amount of energy, not roughly right, exactly right. If the photon's energy is even slightly off, the interaction simply does not happen. The atom ignores it completely. This precision is not a quirk of hydrogen atoms. It is a general feature of quantum systems. The allowed energies of any quantum system are determined by its internal structure, by the geometry of its potential, by the constraints imposed by the uncertainty principle and the rules of quantum mechanics. Change the structure, and you change the allowed energies. Give a quantum dot a different size, and its absorption spectrum shifts. Give a nucleus a different number of protons, and its energy levels rearrange. Every atom, every molecule, every quantum system has a unique signature, a unique set of permitted energies, written into its structure like a fingerprint. This is why spectroscopy, the measurement of the light emitted or absorbed by atoms and molecules, is so powerful. By reading the precise frequencies of light that a sample emits, you can identify exactly which atoms and molecules are present, even in a distant star, even in a cloud of gas light years away. The pattern of permitted energies is a unique identifier, and it is entirely determined by the rules of quantum mechanics acting on the specific physical structure of the system. Energy, in this light, is not something you inject into systems from outside. It is something that emerges from the rules that govern what each system is allowed to be. Let us think for a moment about what it means for energy to travel. In classical physics, energy traveled either by being carried by moving matter or by propagating as waves through some medium. Sound carried energy through air by compressing and rareifying the gas. Ocean waves carried energy through water by displacing and disturbing the liquid. Light was, for a time, believed to travel through the luminiferous ether, a hypothetical medium that filled all of space. That ether was never found. The Michelson-Morley experiment in 1887 looked for it with extraordinary precision and found nothing. Light traveled through empty space with no medium, no carrier, no substrate. This was deeply disturbing to classical physicists. How could a wave propagate without a medium? What was waving? The answer, from quantum field theory, is that the field itself is the medium. The electromagnetic field is not a disturbance in something else. It is itself the entity that vibrates. And when a photon propagates through space, it is not a particle traveling through a field. It is the field itself, locally and temporarily, carrying a quantum of excitation from one place to another. The energy does not move through space like a messenger through terrain. The energy is the disturbance, the excitation, the organized activity of the field. And because the field is everywhere, simultaneously present at every point in space, the propagation of energy through it is not the transportation of a substance, but the spreading of a pattern. This is why energy can exist in apparently empty space. The vacuum is not truly empty. It is permeated by quantum fields in their ground state, buzzing with their irreducible zero-point fluctuations, always and everywhere carrying this minimum irreducible energy that cannot be removed. You cannot reach into a region of space and take away the vacuum energy. You cannot switch off the quantum fields. They are not optional features of the universe. They are the substrate of reality. Everything you can see or touch or measure is built on top of them out of their excitations, from patterns in their activity. Matter itself is, at some deep level, a form of organized energy in quantum fields. Mass, that most apparently solid and substantial of properties, turns out to be deeply connected to energy. Einstein showed this in 1905 with the most famous equation in science, E equals mc squared. Mass is a form of energy. A particle at rest still has energy simply by virtue of its mass. That energy can, under certain conditions, be converted into other forms. In nuclear reactions, small amounts of mass convert into enormous amounts of energy, because c, the speed of light, is an enormous number, and squaring it produces something even more enormous. The energy released by the sun comes from the conversion of mass into energy in nuclear fusion reactions in its core. The energy of nuclear weapons comes from the same principle. Mass is not a separate property from energy. It is energy stored in a particularly stable and condensed form. And this means that the question of what energy is made of circles back on itself in an interesting way. If mass is energy, and if everything that has substance has mass, then asking what energy is made of is a little like asking what matter is made of, and then being told that the answer is energy. The two concepts are not as separate as they first appear. At the deepest levels of our understanding, matter and energy are different expressions of the same underlying physical reality, different aspects of the excitation of quantum fields, different ways that the fundamental fields of nature can organize themselves, interact with each other, and give rise to the enormous variety of structures and processes we call the physical world. This brings us to one of the most beautiful and deepest ideas in all of modern physics, the relationship between symmetry and conservation. In classical mechanics, the conservation of energy had always felt like a brute fact. Energy is conserved because experiments show that it is. But in the 20th century, a German mathematician named Noether proved something that changed the entire conceptual landscape. She proved that every conservation law in physics corresponds to a specific symmetry of nature. That symmetry is not decorative. It is the reason for the conservation. And the symmetry corresponding to the conservation of energy is one of the most fundamental symmetries imaginable: time translation symmetry. What this means is that the laws of physics are the same today as they were yesterday, and the same yesterday as they will be tomorrow. The rules do not change with time. A hydrogen atom forms and radiates and behaves in exactly the same way regardless of when it forms. The laws of gravity work the same on Monday as on Friday. If you perform any physical experiment and then repeat it a week later, under identical conditions, you will get identical results. The universe is, in this deep sense, temporally uniform. It does not favor any moment over any other. The laws are constant. And Noether's theorem says, because the laws are constant in time, energy is conserved. The conservation of energy is not an independent additional rule. It is a mathematical consequence of temporal uniformity. This is staggering. It means that if you want to understand why energy is conserved, the answer is because the universe does not change its rules as time goes by. If the laws of physics were different on Tuesdays than on Mondays, energy would not be conserved. It is the stability of the rules themselves that guarantees the stability of the energy account. And this reframes energy in the most abstract and profound way possible. Energy is not a substance that persists because it is made of something indestructible. Energy is a conserved quantity that persists because the laws of physics are temporally symmetric. It is a mathematical consequence of a deep symmetry of nature. It is a reflection of the timelessness of physical law. Energy, in this view, is less like a material and more like a shadow cast by symmetry. Less like water in a container and more like a number that the universe is compelled by its own logical structure to maintain. This is one of those ideas that, once you have absorbed it, changes how everything looks. When you watch a ball arc through the sky, you are watching time translation symmetry made visible. When a fire burns and light spreads outward and the wood cools to ash, the total energy is perfectly conserved, not because something is keeping track of the material and making sure none leaks, but because the laws governing every electron and every photon in that process are the same laws that governed the same kinds of interactions yesterday and last year and 1 billion years ago. The universe is consistent with itself across time, and that consistency is energy. Now let us dwell a little longer in the quantum world and explore something that many accounts of energy pass over too quickly: the role of interference. Quantum mechanics describes particles not as objects with definite positions and momentus, but as probability amplitudes, complex numbers spread through space whose squared magnitude gives the probability of finding the particle in any given location. These amplitudes interfere with each other in the way waves interfere. Two amplitudes can add together and reinforce, producing a higher probability, or they can cancel, producing zero probability. This interference is not just a mathematical artifact. It is experimentally real and has been demonstrated countless times in electron and photon, double-slit experiments, in neutron interferometry, in experiments with entire atoms and molecules, and interference has consequences for energy. When two quantum amplitudes interfere constructively, the probability of finding the system in a certain state is enhanced. When they interfere destructively, certain states become inaccessible. The energy structure of a quantum system is, in part, a product of how its amplitudes interfere with themselves. Consider a particle in a box, a quantum particle confined between two walls. The allowed energy states are those for which the particle's wave function fits exactly inside the box, completing a whole number of half wavelengths between the walls. These are the states where the wave function reinforces itself under the reflections from the walls rather than canceling. Any wave function that does not fit in this way destructively interferes with itself and disappears. The result is that only discrete specific wavelengths are allowed, corresponding to discrete specific momenta and discrete specific energies. The energy spectrum is not imposed from outside. It emerges from the geometry of the situation and the requirement that amplitudes must interfere constructively to produce stable, persistent states. Energy levels in atoms arise by a similar mechanism. The electron's wave function must fit around the nucleus in a way that permits constructive interference. The discrete allowed energies are the discrete allowed patterns of constructive interference. When you see a sharp spectral line from an atom, you are seeing the signature of a specific interference pattern, a specific mode of self-reinforcement that the electron's wave function can sustain in the field of the nucleus. This perspective connects energy to geometry, to space, to the specific shapes that wave functions can adopt within particular constraints. It makes energy look less like an amount of stuff and more like a characteristic frequency of a resonance pattern, like the pitch of a note that a cavity can sustain. And it deepens the analogy, already hinted at, between quantum systems and musical instruments. An atom is like an instrument. Its geometry, determined by the number and arrangement of its protons and neutrons and electrons, determines the set of allowed resonance patterns. And energy is the label we put on those patterns. The energy levels of an atom are its natural frequencies. When an electron jumps between levels, the atom rings at the difference frequency, and the photon that emerges from that transition is the sound of that ringing, cast out into space to carry the signal of what just happened. The analogy to music is imperfect, as all analogies are, but it points at something real. Energy is deeply connected to oscillation, to frequency, to periodicity. The energy of a photon is proportional to its frequency. The energy of an electron in an atomic orbital is related to the frequency with which its wave function oscillates. The energy of a phonon, a quantum of vibration in a crystal, is related to the frequency of the vibration. The energy of a particle is related to the frequency of its matter wave through the de Broglie relation. Frequency is not just a metaphor for energy. It is the physical reality underlying energy at the quantum level. Higher frequency means more rapid oscillation of the underlying quantum field. More rapid oscillation means more energy. Energy is, in a very deep sense, the rate of change of quantum phase. The higher the energy of a state, the faster its phase oscillates. And the conservation of energy is, in this view, a consequence of the fact that the rate of phase oscillation of any quantum state is fixed by the Hamiltonian, the mathematical operator that generates time evolution. The Hamiltonian is the quantum version of the total energy. It tells every quantum state how fast to oscillate. And when a system is left undisturbed, it oscillates at a steady, fixed rate. The energy does not change because the oscillation rate does not change. Energy conservation at the quantum level is the steadiness of quantum oscillation in the absence of external disturbance. This is not a loose poetic statement. It is a precise mathematical statement about the structure of quantum mechanics. The time-dependent Schrödinger equation, which governs the evolution of all quantum systems, is exactly the statement that the rate of change of a quantum state's phase is proportional to its energy. Energy is the generator of time evolution. It is the quantity that tells the universe how fast to move from one moment to the next. Strip away the historical layers, strip away the Newtonian mechanics and the thermodynamic formalism and the classical field theory. And at the bottom of everything, energy is the rate at which the present becomes the past, the tempo of the universe. And yet, even this extraordinary insight is not the final word. Because there is a regime of physics that we have not yet visited, a regime where quantum mechanics meets gravity, and where everything we think we understand about energy is placed under enormous and unresolved strain. General relativity, Einstein's theory of gravity, describes gravity not as a force, but as a curvature of spacetime. Mass and energy curve spacetime. Objects move along the curves of that spacetime. The sun curves spacetime so deeply that the Earth, following the straightest possible path through curved spacetime, traces an elliptical orbit. Light, following the straightest possible path near a massive star, bends. Time itself runs more slowly near massive objects and more quickly far away. Gravity is geometry, space-time is dynamic. And in general relativity, the concept of energy becomes, to put it gently, complicated. In flat, unchanging space-time, defining energy is straightforward. But in curved dynamic spacetime, the very notion of energy conservation requires careful qualification. Because the symmetry argument that grounds energy conservation, the time translation symmetry identified by Noether's theorem, is a symmetry of flat spacetime. In a universe where spacetime itself is expanding, as our universe is, time translation symmetry is broken. The universe today is not the same as the universe yesterday. It was smaller and denser and cooler. The laws of physics are the same, but the background spacetime is not. And this means that, in general relativity, global energy conservation, the conservation of energy across the entire universe, is not guaranteed in the usual way. Cosmologists wrestle with this constantly. When the universe expands, Photons traveling through it are redshifted. Their wavelengths stretch, their frequencies decrease, their energies decrease. Where does that energy go? The honest answer is that in general relativity, in an expanding universe, it does not simply go somewhere. The concept of total energy that is globally conserved across the whole universe is not well defined in the way it is in flat space-time. This is not a failure of physics. It is a recognition that concepts developed in flat Newtonian space-time have boundaries. They are reliable within those boundaries and unreliable outside them. Energy conservation, as we normally understand it, is impeccably valid locally. In any small region of space-time, over any short interval, energy is conserved to extraordinary precision. The Earth does not suddenly gain or lose energy in a way that violates the local rules. Atoms do not spontaneously violate energy conservation in the quantum mechanical sense. The local laws hold absolutely. It is only when you try to add up the energy of the entire expanding universe that the concept becomes slippery. And this slipperiness points toward the deepest unresolved frontier in physics, the reconciliation of quantum mechanics and general relativity. We do not have a consistent quantum theory of gravity. We do not know how to describe spacetime in quantum mechanical terms without the equations breaking down. And this means that our understanding of energy, which is perfectly precise in the quantum regime and perfectly precise in the relativistic regime, becomes uncertain and contested in the regime where both apply simultaneously. In the extreme conditions near the Big Bang, in the interior of black holes, at the Planck scale where spacetime itself may have quantum structure, at that frontier, even the concept of energy may need to be reconceived. What energy is, at that depth, is genuinely unknown. And this is not a confession of failure. It is a confession of how far we have come and how much further there is yet to go. There is a quality to the deepest questions in physics that is different from the quality of questions in other fields. A historical question, answered definitively, closes. A biological question, resolved by an experiment, settles. But the deepest questions in physics have a way of opening further as you answer them, of revealing deeper questions beneath each answer, of dissolving into abstractions that eventually shake the foundations of what you thought you were asking. The question of what energy is has this quality in abundance. We began thinking we were asking about a substance. We ended up discovering that we might be asking about a symmetry, about a law, about the logical structure of time itself. We began thinking energy was an ingredient of the universe, something the universe was made of. We ended up with the possibility that energy is a description of the universe's rules, a property of its structure, a feature of how reality is permitted to change. This is not a loss. It is the opposite of a loss. It is discovery of the most profound kind. When a concept that once seemed concrete and material is revealed to be abstract and structural, it does not become less real. It becomes more deeply real. It is connected to more things, more intimately, in more profound ways. The move from energy as substance to energy as symmetry is the move from a single room to a whole building, from a single stone to the architecture of a cathedral. The concept has not shrunk. It has expanded. It has deepened. It has found its proper place in the structure of everything. And there is something aesthetically right about where we have arrived. The universe conserves energy not because it is hoarding some precious material. It conserves energy because it obeys the same rules today as yesterday. Because time is not an adversary that changes the game as it passes. Because there is a deep and beautiful consistency woven through the history of the cosmos. Every atom that has ever formed, every star that has ever burned, every particle that has ever collided in a detector has obeyed the same rules, and energy is the ledger that records that obedience. It is the numerical statement of the universe's self-consistency. That is what energy is, not a thing. A truth. Let us now return, briefly, to the quantum vacuum, because there is something about it that deserves more careful attention than it usually receives. When physicists say that the vacuum has energy, they are saying something very specific. They are not saying that empty space is filled with some invisible fluid. They are not saying that there is a hidden medium permeating all of space. They are saying that quantum fields, which exist everywhere and always, have a minimum energy state that is not zero. The fields are always vibrating, always fluctuating, always in some irreducible state of activity even when there are no particles present. These vacuum fluctuations are not theoretical inventions. They have measurable consequences. The Casimir effect, which we have already mentioned, is one, but there are others. The Lamb shift is a tiny but measurable change in the energy levels of hydrogen caused by the interaction of the electron with vacuum fluctuations of the electromagnetic field. It was measured in 1947 by Willis Lamb and was one of the experimental results that drove the development of quantum electrodynamics, the relativistic quantum field theory of electromagnetism. The anomalous magnetic moment of the electron is another measurable consequence of vacuum fluctuations, calculated to extraordinary precision and verified experimentally. These are not marginal effects. They are among the most precisely tested predictions in all of physics. The vacuum is active. The vacuum has structure. The vacuum has energy. And the particles we observe, electrons, photons, quarks, emerge from this vacuum as localized disturbances. They are not primary. The field and its vacuum state are primary. The particles are secondary. This inversion is one of the most radical conceptual shifts in the history of science. We tend to think of matter as the basic stuff and empty space as the absence of stuff. Quantum field theory reverses this. Empty space, the quantum vacuum, is the basic state. Matter is a departure from that state. Particles are excitations above the vacuum. When an electron-positron pair is created from two colliding photons, it is not that new substance is being created. It is that the underlying electron field, which was previously in its ground state at that location, has been promoted to an excited state. The electron and positron are now present as excitations of the field. When those excitations annihilate, the field returns toward its ground state, releasing the energy as photons. Creation and annihilation are not the appearance and disappearance of substance. They are transitions of the field between states of different excitation. Energy is what changes when these transitions happen. Energy is the label on the state of the field, and vacuum energy is the energy of the state, with no excitations at all. The irreducible background hum of a universe that cannot be entirely silent. It is worth pausing here to think about what any of this means for the human experience of energy. Because everything we have discussed, from classical mechanics to quantum field theory to vacuum fluctuations, ultimately manifests in the world we inhabit. The warmth of sunlight on your skin is energy from photons, quantized excitations of the electromagnetic field produced by nuclear fusion reactions in the sun's core, traveling across 93 million miles of space in 8 minutes, absorbed by molecules in your skin and converted into heat. The chemical energy stored in food is energy locked in the arrangement of electrons around atomic nuclei, in the precise configuration of chemical bonds, in the quantum mechanical structures of molecules. When your body metabolizes food, it rearranges those structures, releasing the stored energy in the form of heat and mechanical work and nerve signals. The electrical signals in your nervous system are governed by the movement of ions across membranes, driven by concentration gradients that store energy like springs waiting to release. Your thoughts, whatever they are, wherever they ultimately come from, are patterns of activity in networks of neurons, sustained by the continuous flow of chemical and electrical energy through your brain. Every moment of your experience is energy flowing, transforming, following the ancient and unbreakable rules. You are not outside the physics. You are made of it. You are a localized, temporary, extraordinarily complex pattern of energy in quantum fields, sustained by continuous flow from the sun, through chemistry, through metabolism, through electrical signaling. And when that pattern ends, the energy does not disappear. It disperses. It spreads. It becomes part of the background thermal energy of the environment, slightly warming the air, slightly increasing the entropy of the world. Nothing is lost. The account always balances. The universe continues its patient, relentless bookkeeping, as it has for 14 billion years, as it will for whatever vast time remains. You are here, briefly, as an organized eddy in the great flowing of energy that constitutes the cosmos. And that is not a diminishing thought. It is an astonishing one. Consider the sun for a moment from the perspective of everything we have covered. The sun is a ball of plasma, mostly hydrogen, about 400,000 miles across, sitting at the center of our solar system. It has been burning for about 4.5 billion years and will continue burning for approximately another 5 billion. In its core, temperatures reach 15 million degrees, and pressures reach 250 billion times the pressure of Earth's atmosphere. Under these extreme conditions, hydrogen nuclei, protons, are forced close enough together that the strong nuclear force can overcome their electromagnetic repulsion, and they fuse. 4 protons fuse through a series of steps into a helium nucleus. But the helium nucleus has slightly less mass than the 4 individual protons it was assembled from. The missing mass, about 0.7% of the original mass, is converted into energy according to Einstein's equation. Every second, the sun converts about 4 million metric tons of mass into energy. That energy, initially in the form of gamma rays produced deep in the core, begins a long and winding journey outward. The core is so dense that a photon of gamma radiation might travel only a millimeter or so before being absorbed and re-emitted in a random direction. This random walk from core to surface takes, on average, about 100,000 years. Then the photon escapes into space. 8 minutes later, some of those photons reach Earth. They warm the oceans. They drive the water cycle. They power photosynthesis, which stores their energy in chemical bonds. Those chemical bonds are later released by animals and plants and fires, driving the countless processes of the biosphere. The energy that began as the mass of 4 protons in the sun's core, converted through nuclear physics into radiation, transformed through stellar opacity into surface photons, transported through space, absorbed by a leaf, chemically stored, metabolically released, flows eventually into everything alive on this planet. It is the same energy, differently organized at every step. And at every step, the account balances. Not approximately, exactly. The conservation of energy is not an approximation or a tendency. It is a feature of the deep structure of physical law that is held without exception across all of cosmic history. When you appreciate that, when you really feel the weight of it, the question of what energy is becomes something close to the question of what reality is. We have arrived after this long journey at a picture of energy that is very different from the one most people carry with them. Energy is not a glowing substance inside batteries and fuel cells. It is not a fluid that flows from hot things to cold things. It is not a material ingredient out of which physical events are assembled. It is the quantity that the universe conserves because its laws are consistent in time. It is the label on the permitted states of quantum systems. It is the measure of activity in quantum fields. It is the rate at which quantum states evolve. It is the shadow cast by symmetry. At human scales, energy looks like a thing that food contains, that motion involves, that fuels release. And at human scales, treating it as a thing works perfectly well. But at the edges of human scale intuition, in the quantum regime and the relativistic regime and the cosmological regime, the thing-like appearance falls away and the deeper truth becomes visible. Energy is a structural feature of physical law. It is one of the ways the universe stays internally consistent as time passes. It is the numerical measure of the capacity for change, not change itself, not the cause of change. The measure of how much change is possible in a given physical configuration. And it is conserved not because something is being preserved, but because something is being obeyed. The law that says change your configuration, exchange your excitations, transform your forms, but always in a way that keeps the total measure constant, always in a way that respects the deep time translation symmetry, always in a way that honors the consistency of the universe with itself. This is what energy is, not a thing, a discipline, a constraint, a logical consequence of the universe's self-consistency. And somehow, from this abstract foundation, everything physical rises, motion and heat and light and chemistry and thought and stars and time. All of it built on the insistence that the laws of nature do not change, that the measure of change is conserved, that the universe is not allowed to contradict itself. Every star burning in the sky above you tonight is doing so under this constraint. Every particle in your body obeys it. Every thought crossing your mind is governed by it. The most ancient and the most fundamental of the universe's disciplines, written into the structure of time itself, expressed in the conservation of energy, playing out in every process, every moment, everywhere in the cosmos. Before we come to a close, There is a dimension of this story that we have barely touched, and it may be the most humanly important dimension of all. It concerns not the physics of energy, but the history of energy, how the understanding of energy shaped human civilization, how it drove the Industrial Revolution, how it underlies every technological achievement of the modern era, and how the challenge of energy, specifically the challenge of where humanity gets its energy and what it does with it, may be the defining physical challenge of our time. Because every machine that has ever run, every city that has ever been lit, every vehicle that has ever moved, every computation that has ever been performed has consumed energy, not destroyed it. The first law of thermodynamics remains inviolate, but converted it from useful low-entropy forms into less useful high-entropy forms, into waste heat, into disordered thermal energy dissipating into the environment, and that conversion has consequences. The second law of thermodynamics, the one that says entropy always increases, the one that defines the direction of time, the one that says useful energy can only be used once before it degrades, is as relentless as the first law. You cannot create energy and you cannot get it back after it has spread. You can only transform it from ordered to disordered, from concentrated to diffuse, from useful to useless. Understanding this at a civilizational level is not optional, it is urgent. The Earth receives an enormous flux of solar energy, about 173,000 terawatts of sunlight, constantly illuminating the planet. Global human civilization currently consumes about 18 terawatts. The sun is delivering 10,000 times more energy to Earth than humanity uses. The question of energy scarcity is not a question of whether there is enough energy available. There is vastly more than enough. It is a question of how to capture it, how to convert it into useful forms, how to store it and distribute it with acceptable efficiency. These are engineering and political challenges, not physics challenges. The physics is, in this sense, already on our side. The sun will keep shining, the energy will keep arriving. The universe is not running short of energy on any time scale relevant to humanity. What matters is what we do with what arrives, and that is, at its root, a question about entropy. A question about the rate at which we convert ordered, concentrated, low-entropy energy into disordered, diffuse, high-entropy waste. The slower and more carefully we do that conversion, extracting maximum useful work per unit of entropy increase, the more sustainably we can run the machinery of civilization. Thermodynamics is not just an abstract physics topic, it is the physics of survival. The reason any engine has a maximum possible efficiency, famously quantified by Sadi Carnot in the 1820s, is fundamentally a statement about entropy. The Carnot efficiency sets an absolute ceiling on how much useful work can be extracted from any heat engine operating between two temperatures. No engineering can exceed it. No clever trick can get around it. It is as fundamental as the conservation of energy itself, and it applies not just to steam engines and internal combustion engines, but to every energy-converting process in nature. The efficiency of photosynthesis, the efficiency of mitochondria in your cells, the efficiency of the sun in converting nuclear energy into radiation. Everything that converts energy from one form to another does so within the constraints set by the second law. This makes thermodynamics one of the most practically powerful bodies of knowledge ever assembled. It tells you, without needing to know any engineering details, what is and is not possible. It draws hard boundaries that no amount of ingenuity can cross. And understanding where those boundaries lie is essential for designing the energy systems of the future. Fusion power, if it can be made to work at scale, offers the possibility of abundant low-carbon energy from the same process that powers the sun. The fusion of hydrogen into helium, with the conversion of a tiny fraction of mass into an enormous amount of energy. Physicists and engineers have been working on controlled fusion for more than 60 years, and while the challenges are formidable, recent advances have brought the goal measurably closer. Solar panels convert photons directly into electrical current through the photoelectric effect, the very quantum phenomenon that Einstein used to argue for the photon. Wind turbines convert the kinetic energy of air masses, which is ultimately solar energy deposited in the atmosphere through differential heating, into electrical energy. All of these technologies are, at their core, applications of the physics of energy we have been exploring throughout this narrative. They are the human attempt to align civilization with the physics of the universe, to harness the flows of energy that the cosmos provides on scales vast beyond any individual comprehension. And there is something deeply moving about that attempt, because the science that enables solar panels and fusion research and the understanding of thermodynamics that guides energy efficiency, all of it is the product of the same human impulse that has driven physics throughout its history. The desire to understand, the desire to know what is really happening, not just what the rules are, but why the rules are what they are. The desire to follow the question wherever it leads, even when it leads somewhere uncomfortable, even when the answer turns out to be stranger than anyone expected. The history of energy and physics is, in one sense, a history of successive disappointments. Each time we thought we understood what energy was, we discovered that our understanding was incomplete. The caloric theorists were wrong. The proponents of a smooth, continuous energy were wrong. The early quantum physicists who thought Planck's constant was just a calculational trick were wrong. The classical field theorists who thought light could be fully described without reference to photons were wrong. Each disappointment was followed by a deeper understanding. Each collapse of a simpler picture opened a door to a richer one. This is how physics works. Not by accumulating comfortable confirmations, but by probing the edges of the known until the edges crack, and then rebuilding on what is revealed beneath. And the picture that has been built through 2 centuries of increasingly precise and increasingly surprising experiments is one of astonishing coherence and depth. Energy is conserved because time translation symmetry holds. Energy is quantized because quantum mechanics applies to fields. Energy exists in the vacuum because the uncertainty principle forbids perfect stillness. Mass is a form of energy because spacetime is dynamic and the relationship between matter and the geometry of spacetime is encoded in Einstein's field equations. All of this hangs together. All of it is connected. All of it points toward the same underlying truth. The universe has a logical structure, and energy is one of the clearest expressions of that structure. When physicists search for a unified theory that reconciles quantum mechanics and general relativity, they are, in part, searching for a deeper understanding of energy. They are trying to answer the question of what energy means in a regime where space-time itself is quantum mechanical, where the geometry of space is subject to the same uncertainty principles that govern particles. That question does not yet have an answer, but the search for it is one of the great ongoing adventures of the human intellect, and it will not stop until the answer is found. Let us spend a moment with black holes, because black holes are perhaps the place where our understanding of energy is most severely tested, most beautifully expressed, and most deeply mysterious. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The collapse is violent, sudden, and total. For a star massive enough, nothing can stop it. Not the pressure of hot gas, not the quantum degeneracy pressure of electrons, not even the degeneracy pressure of neutrons. The collapse continues until the matter reaches a state of such extreme density that the curvature of spacetime becomes infinite at a point called the singularity. Around the singularity lies the event horizon, the boundary beyond which nothing, not even light, can escape. The black hole sits there, massive and dark and profoundly strange, warping spacetime around it, bending the paths of light and matter that pass near it, consuming anything that falls within its grasp. For decades after black holes were predicted by general relativity, they were believed to be perfectly black, to emit nothing, to absorb everything, to exist forever, once formed. Then in 1974, Stephen Hawking made a calculation that changed everything. He applied quantum field theory to the curved spacetime around a black hole and found something astonishing. The black hole was not perfectly black. It was glowing, faintly, almost imperceptibly, but glowing. The mechanism behind this Hawking radiation, as it came to be called, is deeply connected to everything we have discussed about vacuum energy and quantum fields. In flat spacetime, the quantum vacuum is well defined. All observers in inertial motion agree on what constitutes the vacuum, the ground state of the fields with no particles present. But in curved spacetime, near a black hole, this agreement breaks down. What one observer calls the vacuum state, another observer in a different gravitational situation calls a state containing particles. The vacuum is observer-dependent in curved space-time, and near the event horizon of a black hole, this difference becomes a real, physical phenomenon. The black hole emits thermal radiation, with a temperature inversely proportional to its mass. A stellar mass black hole radiates at an unimaginably low temperature, far colder than the cosmic microwave background, and so in practice it absorbs far more energy from its surroundings than it radiates. But a very small black hole, a primordial black hole formed in the early universe, would be much hotter and would evaporate much more quickly. As a black hole radiates, it loses mass, it shrinks. Its temperature rises, it radiates faster. Eventually, in a process that takes an unimaginably long time for any black hole that forms from a stellar collapse, the black hole evaporates completely. The mass, the matter, the information that fell into it, all of it gone. Or is it? Here we arrive at one of the deepest unsolved problems in physics, the black hole information paradox. Quantum mechanics, at its core, is a theory that preserves information. If you know the quantum state of a system at one time, you can in principle calculate what it was at any earlier time. Information is never truly destroyed. But if matter falls into a black hole, and the black hole eventually evaporates in purely thermal Hawking radiation, then the information about the detailed quantum state of that matter appears to be lost forever. The thermal radiation carries no information about what fell in. This seems to violate a fundamental principle of quantum mechanics. Either Hawking radiation is not purely thermal and carries hidden information somehow, or quantum mechanics itself breaks down in black hole evaporation. Or there is a third option nobody has clearly identified. This is the information paradox, and it has been the subject of intense theoretical debate since Hawking first pointed it out. The debate has produced profound insights about the relationship between quantum mechanics, gravity, space-time, and information. It has led to the development of ideas like the holographic principle, which suggests that the information content of a region of space is encoded on its boundary rather than its volume, and to the idea that space-time itself may be emergent from quantum entanglement rather than fundamental. These are extraordinary ideas, and they are all at their root about energy and information and what happens to them at the most extreme physical conditions. The black hole is where quantum mechanics and general relativity collide most violently, and the sparks from that collision are illuminating some of the deepest features of physical reality. One of those features is the relationship between energy and information, which turns out to be far deeper than it appears at first. Information, in the technical sense used by Claude Shannon when he founded information theory in 1948, is a measure of surprise, how much you learn when you receive a message, quantified in terms of how unexpected the message was. Shannon showed that information could be precisely quantified, and that there were fundamental limits on how efficiently information could be transmitted or stored. And later, physicists showed that information is not just an abstract concept, it has physical consequences. There is a minimum amount of energy required to record a bit of information, to register a distinction between two physical states. This limit, called the Landauer limit after Rolf Landauer, who derived it in 1961, connects information directly to thermodynamics. Every time you erase a bit of information, you must dissipate at least a small amount of energy as heat. The entropy of the universe increases. The physical act of forgetting has an irreducible thermodynamic cost. This is a remarkable result. It means that computation, the processing of information, is subject to thermodynamic constraints. It means that the laws of physics set a fundamental limit on how efficiently any computer can operate, not as an engineering limitation, but as a consequence of the connection between information and entropy. Your brain, your smartphone, the servers running the internet, all of them are subject to Landauer's limit. They consume energy to process information, and that energy consumption is bounded below by the thermodynamic cost of the logical operations they perform. Information is physical. Energy and information are deeply entangled concepts. And in the context of black holes, where information paradoxes arise, this entanglement becomes a source of profound theoretical tension. If the energy content of a black hole is encoded in Hawking radiation, but the information about what fell in is lost, then there is an inconsistency between quantum mechanics and thermodynamics that has no simple resolution. The search for that resolution is driving some of the most creative and ambitious theoretical work in contemporary physics. We might also pause to wonder about dark energy, one of the most mysterious discoveries in the history of cosmology. In 1998, two independent teams of astronomers measuring the distances and recession velocities of distant supernovae made a shocking discovery. The expansion of the universe, which everyone expected to be slowing down due to the gravitational attraction of all the matter in the universe, was actually speeding up. The universe was accelerating in its expansion. Something was pushing the galaxies apart, overcoming the pull of gravity on the largest scales. That something was named dark energy, and it constitutes about 68% of the total energy content of the universe. Dark matter, the mysterious unseen substance that provides extra gravitational glue holding galaxies together, makes up about 27%. Ordinary matter, everything we have ever seen or touched or measured, all the stars, planets, gas clouds, black holes, and everything else, makes up only about 5% of the total. We are a small minority in an energy budget dominated by things we do not understand. Dark energy is one of the deepest mysteries in contemporary physics. The simplest candidate for it is the cosmological constant, which Einstein originally introduced and then abandoned, which represents a constant energy density of empty space, precisely the vacuum energy we have been discussing. But when you calculate the expected vacuum energy from quantum field theory and compare it to the measured value of the cosmological constant, you get the discrepancy of 120 orders of magnitude that we mentioned earlier. Something is wrong with that calculation. Something is not understood. There are other candidates for dark energy: scalar fields slowly rolling down their potential, modifications of general relativity at large scales, quantum corrections to gravity. None of them is fully satisfactory. None of them has been definitively confirmed by observation. Dark energy remains a mystery, and since it constitutes nearly 70% of the total energy of the universe, the mystery is not a minor one. We do not understand the nature of the dominant form of energy in the cosmos. This is humbling, but it is also, in the best scientific tradition, an invitation, a door left open by the universe, waiting for the right key. There is one final concept worth exploring before we come to rest, and it is the concept of energy in living systems. Life, as far as we know, is the most complex organized phenomenon in the universe. A living cell is an enormously intricate network of chemical reactions, all interlinked, all running simultaneously, all precisely regulated, all consuming and transforming energy with extraordinary sophistication. The cell does not violate thermodynamics. No living system does. The second law holds everywhere. Entropy is produced by every metabolic process. But living systems maintain their internal organization by continuously importing low-entropy energy from the environment and exporting high-entropy waste. They are not equilibrium systems. They are far from equilibrium systems sustained by continuous energy flow. A bacterium importing nutrients from its surroundings, oxidizing them in metabolic reactions, using the released energy to drive cellular processes, and exporting waste products is, from a purely physical standpoint, a thermodynamic engine. It takes in low-entropy chemical energy and produces high-entropy waste. The difference in entropy between what comes in and what goes out is greater than zero, consistent with the second law. But along the way, it uses that entropy production to maintain and reproduce its complex internal structure. Life is not magic. It does not circumvent physics, but it is extraordinarily clever at working within physics. The molecular machines of life, the protein motors that transport cargo within cells, the ATP synthase that captures the energy of proton gradients to synthesize the cell's energy currency, the ribosome that reads genetic information and assembles protein chains. All of these are nanoscale machines operating at the thermal noise limit, using precisely the right amount of energy to do their work in a world where thermal fluctuations are constantly jostling everything. The theory of how life manages energy, how it achieves the organized complexity that defines it, despite the constant thermodynamic tendency toward disorder, is one of the most active and exciting areas of biophysics. It connects quantum mechanics through the quantum effects that appear to play a role in photosynthesis and enzyme catalysis, to the second law through the entropy production that underlies all metabolism, to to information theory, through the information processing that DNA and the genetic code represent, to evolution, through the selection pressure for ever more efficient and robust energy management. And it reminds us that energy is not just a concept for physicists and engineers. It is the business of life. Every living thing is an expression of the universe's capacity to organize energy into structures of sustained complexity. And the fact that we can think about this at all, the fact that minds have evolved that are capable of formulating and understanding the concept of energy, is itself a product of billions of years of biological evolution, driven by energy flow from the sun, through chemistry, through metabolism, through neural computation. We understand energy partly because energy, over geological time, has organized itself into minds capable of understanding. There is one more thing worth saying, and it concerns the nature of questions themselves. When we ask what energy is made of, we are importing an assumption that everything real must be made of something else, that the chain of composition never ends with an abstraction. But the history of physics teaches a different lesson. The deepest realities are not made of anything else. They are the ground. They are the bottom. They are the places where the question of what something is made of ceases to apply, and is replaced by the question of what role this thing plays in the structure of nature. Energy plays a role so fundamental that asking what it is made of is a little like asking what mathematics is made of, or what logic is made of. The question dissolves not because it cannot be answered, but because the concept in question is not the kind of thing that has a material composition. It has a structural position. It has a logical role. It has a deep relationship with the architecture of time and law and change. And that, perhaps, is the deepest lesson the history of energy has to teach. Some of the most real things in the universe are not made of anything. They are not smaller than the smallest particle. They are not located at any particular place. They do not sit inside objects waiting to be found. They are patterns, rules, structures of permission and constraint, relationships between states and transitions. They are real not because they have substance, but because they have consequences. Energy has consequences. Enormous, measurable, precise, universal consequences. It governs every physical process that has ever occurred. It connects the nuclear fire of the sun to the warmth of your skin, the motion of electrons to the signals in your nervous system, the vibration of quantum fields to the Casimir force between two metal plates in a laboratory. It is woven through everything, not as a material thread, but as a logical one. And following it, from fire to quantum vacuum, from Newton to Noether, from caloric fluid to quantum field theory, is one of the greatest intellectual journeys in the history of human thought. A journey that started with the question of what makes things happen and ended with the discovery that the capacity for things to happen is itself one of the universe's most fundamental properties. Not a thing among things, a condition for things at all. There is something specifically worth noting about the way children encounter energy before they encounter physics. A child running at full sprint across an open field understands something about kinetic energy that no equation can fully capture. The feeling of speed as liberation, the total commitment of the body to pure motion. A child leaning close to a fire understands radiant heat without knowing that it arrives in photons. A child watching a thunderstorm feels the crackling tension in the air, the sudden brilliant arc of lightning, the rolling percussion of thunder, and knows viscerally that something enormous is happening, that the sky is releasing something it had been holding. These experiences precede all formalism, and they do not become less true when formalism arrives. What changes is depth. What changes is the understanding of how these experiences connect to each other, to the sun, to the atom, to the quantum vacuum. The child running becomes an adult who understands that the chemical energy in glucose molecules, produced by photosynthesis from sunlight, is being converted through metabolic processes into the mechanical kinetic energy of muscles and limbs. The child warming herself at the fire becomes an adult who understands that the photons arriving on her skin were emitted when hydrocarbon molecules broke their chemical bonds in exothermic reactions, releasing energy stored originally in carbon atoms forged in long-dead stars. The child watching lightning becomes an adult who understands that the discharge represents the sudden equalization of a charge separation, built up by the mechanical collision of ice particles in a storm cloud, with an energy equivalent to exploding about 1 billion joules in a channel of superheated plasma mere centimeters wide. The wonder does not diminish. It deepens, it becomes richer, it extends in more directions. And the direction in which it extends most dramatically is the one we have been traveling all through this narrative: inward, downward, toward the substrate, toward the rules, toward the structure that lies beneath appearances and makes everything possible. That direction always leads, eventually, to energy. Rest now in that thought. Let the universe keep its own accounts, as it always has and always will, long before any mind arrived to notice, and long after the last star has cooled, and the last black hole has evaporated, and the last faint glow of Hawking radiation has spread across the cold and vast and quiet dark. The energy will still be there, diffuse and formless, and spread to its maximum entropy, but perfectly conserved, obeying the ancient rules, honoring the symmetry, consistent with itself across all of time. Nothing lost, nothing gained, only transformed, only flowing, only following, as it has always followed, the deep and patient grammar of the cosmos.